slides, I don't have too much to tell you other than you should note that really we're just presenting the performance package from last semester that covers our short field takeoff and landing. There are some areas where we don't go into as much detail, but essentially it covers all the same things. There's a bit of an intro about why we need to calculate this. We talk about all the different factors and the ways that you can comply with determining there's a safe distance for takeoff and landing. And then we actually run through a P chart. Essentially, it's the performance package. So be assured that you learned all of that last semester, so it's really now just actually learning how to use the PowerPoint. For your own knowledge, sometimes short field takeoff and landings are called maximum performance takeoffs and landings. I don't know what the CAA calls them, I can't remember, but often they are referred to by that name as well. In terms of where to do this lesson, it's abnormal to teach it the way we do. You do not usually teach short field takeoffs to a student as early as we teach it to you guys. Why do we do that? Probably because we're under equivalence and we have to do everything a lot earlier with our students. Typically though, this would be done after solo consolidation has been completed and after force landings, overhead joins, possibly after things like steep turns, wing drop stalls. It depends. There's a bit of variation, like if it's too rubbish on the day your student comes in to do wing drop stalls or steep turns, then you might elect to just stay in the circuit and do these. It is a circuit-based lesson, and you typically teach short field takeoff and landing in the same lesson, not how we teach it here at Massey, because you know we introduced the takeoff in part 1 here, and then it's part 2, I think we do the short field landing, isn't it? So that's pretty abnormal to do it that way, just so you know. What else can I tell you instructional techniques wise? You'll see as we get towards the end of the briefing, there is a P chart that will pop up and it already has the calculations done on it. What I tend to do is as we get to the factors, after I've talked about the factor, I fill in that relevant section of the P chart and I guide them through how to do that. So what I generally have is one of these up here with me, and when we get to say the pressure, altitude and temperature bit, I fill it in, I put it on the document scanner so everyone else can see it, and then they fill it in. And so every time we complete a factor, we go through what it looks like, what it tells us on the graph, and then we actually plot it. But you don't have to do it that way. If you don't do it that way, you're going to get to the end of the briefing and you're going to have to then guide them through the full P chart. So it's up to you where you do it. If you do build the P chart as you get to each factor, don't forget to go back to it and do each factor, because it's really easy to get to the end of weight and then forget to go to the P chart and just move straight on to the next factor. So don't forget that. Probably worthwhile you taking 5 minutes to prepare some resources before you start presenting. So in the background, I've brought up AC 91.3 because you're going to show them that. I've brought up the AIP, specifically COFI aerodrome, because the P chart in this briefing is for COFI aerodrome. And obviously have P charts available for all of your students and get the document scanner ready to use. Do all of that before, because otherwise it gets irritable waiting for people to set up that stuff and going to collect the P charts from another room. You'll see that the ear exercise of this briefing is one slide. It's actually the smallest part of this briefing as a whole. And in a way, it's the least important bit, because today is huge about awareness and building decision making, hence why we talk so long about factors. So you can mention that to them in the introduction as well. That's really all I think I need to say for instructional techniques. The short field landing briefing is a little bit easier, it's a little bit more simplified. This is the one where you've got to give a bit more detail. Probably 45 minutes, I would say, for the briefing. Okay, so today we'll have a look at short field takeoffs and landings. We'll have a break between those two briefings. It'll take us about 45 minutes to get through this first one. So far we've only had a look at normal What we're not talking about is a runway where we haven't calculated that there is a safe distance. We are just talking about a runway where the margin between the takeoff distance required and the takeoff distance available is a lot smaller than what we're used to. For example, all your training so far, we've been using the main sealed runways, 2,000 meters, heaps of distance available. Whereas if we use the grass runway, that margin is much reduced. Today is huge on developing your awareness of the many different factors that affect the takeoff distance, so you can develop a healthy awareness of those in flight and their impact on the takeoff distance. And you'll see we discuss all of these same things in the short field landing briefing as well. So there is a rule in Part 91 that says the pilot in command is responsible for the safe operation of the aircraft and its occupants. So there are a range of situations where we do need to actually physically calculate the distance required for our takeoff. Here's our objectives, have a read of those. This is the first 2 of 3. So as I said, today's all about developing your awareness of how the different factors affect the takeoff distance. But the second part is you've got to be able to make a decision at the end of calculating the distance, whether or not it is safe for you to actually take off today on this runway. Here's our third objective. Have a read of that. Often a manufacturer will specify a short field takeoff and landing technique in the flight manual. Bit of a tangent, but is there one specified in a DA40 flight manual? For takeoff, it describes a technique. For landing, it does not. Why would that be? This is not something to ask your students, but background knowledge. What does that tell you about this aeroplane? If the manufacturer has not bothered to write a short field landing technique in the flight manual, what does that tell you about the aeroplane?
They can already stop in short distances?
Actually the opposite. They were not designed to stop in short distances. Hence why the group rating is so high. You know, it's pretty unusual for a 4-seat aeroplane to have a group rating as high as 8. 172s are typically 4 or 5, and they weigh the same. So it's unusual. So that's the reason. These were European-built aeroplanes designed for long, sealed runways, not for the short grass runways with slope that we often have in New Zealand. So that's just a tangent. You don't have to go through that with your students. So let's discuss some considerations. This is an aerodrome we've been to in your training. It may look a little bit different than it does now. These trees are no longer there, but this is Fox Point. So let's talk about when we actually need to use a short field takeoff technique. This is just a summary of when we might use this technique, and we're going to expand on these things and what it all means in the future slides. So we might choose to do a short field technique when the group rating number is not valid. We'll talk about group rating in the next couple of slides. Maybe the runway is quite short. Obstacles, take a look at the end of the runway here. You can see some trees there. Now they look reasonably far away, but it's surprising how much distance is required to A, get airborne, and B, clear obstacles in the climb out path. So we may elect to do a short field takeoff technique for that, and as part of that, calculate that there is a safe distance for us to climb above those trees. Also in situations where we're expecting our takeoff performance to be poor. Now this might be when it is a really hot day, when the density is low, when the engine performance is poor. So you'll need to think about that in summer. And also for commercial considerations. We may be operating later on when you've got your licenses and you're a qualified pilot, you may be operating for a commercial business, had a lot of passengers on board and need to operate from a short airstrip in unfavourable conditions. That might be a reason for doing a short field takeoff, as well as calculating that as well. So what exactly is takeoff distance? It comprises of two parts. It comprises the ground run, where the aeroplane is physically on the ground to the point where it gets airborne, and then the actual takeoff distance includes the part of the runway where you are climbing to 50 feet once you are airborne. Now our diagram here perhaps doesn't give it justice, but this little distance in here between the point of getting airborne and climbing to 50 feet can be significant on some days. Sometimes it is almost the same distance as what was actually required to get airborne. And we'll hopefully see that in the calculation we perform later on. So it's not just the physical distance that we're on the ground that we need to account for, it's the distance to climb to 50 feet as well. And that will change depending on conditions and depending on the aircraft. There are a number of ways that we can determine whether or not a runway is suitable for us to use for takeoff today. One of those is to use flight manual data. Now, there's lots of different data that might be comprised in the flight manual of the aircraft you're flying. Sometimes an aeroplane flight manual will have performance charts. Tangent here, at Massey, we often have introduced students to P-charts before we do this briefing out of necessity, because our syllabus has us going to some aerodromes where a P-chart may actually be required. So sometimes we've actually done a tutorial and taught them how to do P-charts already. In the industry though, that's abnormal as well. Usually this is the first time you are introducing them to this calculation. So flight manual data might be in the form of a P-chart, which we'll have a look at shortly. It could be a series of tables, and when you start flying the DA42, you'll see it has a series of tables with different factors that you can use to determine the takeoff distance. The flight manual may even specify a given distance for takeoff based on a certain standard conditions, to which we then have to apply correction factors. And that's what is meant by Advisory Circular 91.3 there, which I'll show you very shortly. During your career, you'll no doubt see Case 04 P-charts in some of the aeroplanes you fly, particularly Cessnas. Any aeroplane that is imported into the country prior to, I think it was about 1990 or 1991, was given a performance chart by the CAA to determine the takeoff and landing distance. It accounts for many of the same factors that our own P-charts actually account for. If your aeroplane has one of those, you can still use that today for daily private operations, but we don't have a Case 04 chart for a DA40. And then there's the group rating system. That is the third way that we can determine whether a runway is safe for us to take off on. So what I'll do now is I'll project a C91.3 here, and you can have a more thorough read of this in your own time, but I just want to draw your attention to, it mentions in here that it's an acceptable means of compliance with Rule 91.201, which is the PIC is responsible for the safety of the aeroplane. In here it describes those three different means of determining the runway is suitable for a takeoff and for a landing. So I'll just scroll through so you can see that information there, and you can read through it in your own time, because I'll just talk about it as we go through this briefing. What I will point out at this point though, before it mentioned in the PowerPoint that if we're using a P-chart, we also have to use correction factors from AC 91.3. So here's a table with those correction factors in there, see under the aircraft flight manual data. Often a P-chart doesn't account for all of the different factors that can be quantified that affect the takeoff distance. So we have to come to this little chart here and make some corrections based on the surface type and even the surface condition that we are taking off on. There's a little bit about surface condition as well as slope further on down here. So have a read of that in your own time. Sometimes a manufacturer has specified correction factors of their own, and in the DA40's case, Diamond has. If the the manufacturer has specified factors, you use the manufacturer's ones. You only use the AC 91.3 ones if there are none specified by the manufacturer. Okay, so familiarise yourself with AC 91.3 in your own time. Really important document for you to have a working knowledge of. So let's talk about the group rating system. This is unique to New Zealand. Every aeroplane that is imported into the country now is given a number from 1 to 8, and it indicates the typical performance or the takeoff distance required of this aeroplane. A low number, for example 1, indicates the aircraft has good takeoff performance, as in it can get airborne in a short distance. A group rating that is higher, say 8, indicates an aeroplane that needs a long distance to take off. And the other resource that you should bring in here is a flight manual, which I forgot to get from the FIC room. So grab the flight manual out so that at some point of this briefing you can show your student where to find the group rating for the DA40. Obviously you can't give every student a flight manual, so it might be something you project up here on the document scanner or access the flight manual from FP Web. So as we've just seen here in the flight manual, the group rating for the DA40 is 8. So it does not have good takeoff performance. Each runway is also given, or each evaluated runway is also given a number from 1 to 8. A runway that has a lower number is shorter, and a runway that has a bigger number is longer. Now we can use the group rating system to determine if a runway is suitable to land. We can land on that runway if the number of the runway is equal to or greater than that of the aeroplanes. So for a DA40 with group 8, that means we can only take off and land on runways that are group 8 if we are not intending on doing a P chart. Anything less than that and a calculation is required. So you can find the group rating number on the operational data page in the AIP. So we're going to be talking about Ko-Fi aerodrome today, so I'm going to use this aerodrome for my example. On the operational data page here, you can see the GP column gives you the group rating of the runways for takeoff and for landing. The top line here for runway 09 indicates the group rating for takeoff, and the lower one is for landing. So you can see the takeoff distance specified here and the landing distance specified over here in this box. So sometimes a runway will have a different group rating number for takeoff and landing, and that's because of the displaced thresholds. So take a look at this diagram here. For takeoff, if we're taking off on runway 09, we can go all the way back to the physical end of the runway and use all of the runway for takeoff. So it has a group rating of 6 for its takeoff, but for landing on runway 09, we're not allowed to land before this displaced threshold. So the runway length is reduced, and so the group rating for landing has been reduced. For the opposite runway, taking off, we have to be airborne by that upwind threshold. So it's got a reduced group rating for takeoff, but for landing on runway 27, we can roll all the way to the physical end of the runway, so the group rating for landing is bigger. So it's a really quick and convenient way of determining, without a need for calculations, whether or not you can land or take off on a particular runway. It is based on taking off and landing into wind, and it takes into account the runway length as well as any slope that the aerodrome has. So group 8 for a DA40. And that varies from aircraft to aircraft, so it's important for you to get to know what it is for the aeroplane that you're flying today. So now we've got a bit of an idea of what we need to calculate and how to calculate it. It's time for us to start discussing the different factors that may affect the distance required to take off. So firstly, let's talk about pressure. Pressure is, and you could ask, remember they haven't done mechanics, so you may actually have to guide them through what pressure actually is. Pressure is just the weight of the air molecules bearing down on something. So think back to the performance package. Remember, I would have drawn, there's no blue pen, so it'll have to be So you can think of air pressure as being the weight of the air molecules. So I've drawn the surface of the Earth here. We've got someone who's stood at sea level, and then we've got someone on the top of Mount Everest. The person on the top of Mount Everest is experiencing lower air pressure because the higher we go in the atmosphere, the less air molecules there are and the lower that the pressure will be. So higher pressure towards the surface. Pressure is important because it affects the forces. It affects the thrust, the lift, and the power produced by the aeroplane. So if the pressure reduces, it is as if the aeroplane is flying at higher altitude, where performance reduces, and this will indicate that we need a longer takeoff distance. So up to you how you handle these slides. I prefer to talk about things and then click and bring up what is on the slide and just summarize things. It's up to you, otherwise you can just click and expand on what's there. So decreased pressure indicates a higher pressure altitude. Years ago, a study was done to find an average of the global conditions of temperature, pressure, and density, as well as how those things change as we climb through the atmosphere. And so they developed what is called the International Standard Atmosphere. It's a yardstick for calculating and comparing the performance of the aeroplane in relation to the flight manual on a given day. What they found is that for every, at sea level, the average QNH was 1,013 hectopascals, and it reduced by 1 hectopascal per 30 feet as you climb through the atmosphere. When we're calculating our pressure altitude, we also have to factor in the elevation of the runway, not just the pressure of the day, but also the elevation that we are taking off from. And there's a really easy way to calculate our pressure altitude. Here it is here. And construction technique wise, if you have a look in, which slide would it be? It's going to be under the methods slide. It'll give you some data down in the speaker notes there. So you can actually write that up onto the board, so you're going to base all your calculations on that from now on. So I'll write those up so we can refer back to them. Can someone just read them out to me? So NZKY, what's the first thing? Sorry?
1010 Pascal.
1010 hectopascals. Yep.
30 degrees Celsius. 1150 kilograms. No wind. 7 centimeter dry grass. And 1.1% uphill slope. And bracket NZAIP.
And the elevation, I think, was 810 feet. So we're going to use this data for examples as we go through. So how about you use the formula over here. To calculate what our pressure altitude would be. So get them to do that. What is the answer? Has someone calculated it? This back.
900 feet.
so our pressure altitude, you calculate it is 900 feet. So, even though the physical elevation of the runway, the elevation that we're taking off from is 810 feet, the aircraft and the engine will be performing as if it is flying already at an altitude of 900 feet, where we just learned the pressure is lower. So what does this mean for us? Why do we care? Pressure is lower, pressure altitude is higher, performance is reduced, takeoff distance is longer. So that's what I've illustrated in my diagram. This should all ring a bell from when we did the performance package last semester. So don't forget to always summarise the effect of these factors as you get to them. At the end of the slide would probably be the best place. So pressure altitude is important. Now take a look at this. This is over in the United States at an airfield that has an elevation of 8,500 feet. It was also in the middle of summer where the temperatures in the States can get really high. So we'd expect the aeroplane here to have a very high pressure altitude. Physical elevation, 8,500 feet. And then the temperature is also really hot. We'd expect the performance to be pretty poor. So this might be an example of where a short field takeoff and landing technique could be employed. Note the obstacles around as well. We've got some trees at either end of the runway. We've obviously got some mountains around us. So it's not just the ambient conditions or the weather of the day we have to account for, it's the elevation of the aerodrome as well. Really important to consider both. We also need to factor in the density altitude to consider that. Density is the amount of molecules of air in a given volume, and as we fly higher in the atmosphere, the number of molecules reduces, and just as with pressure, the performance of the engine and the aeroplane starts to reduce as well. Density is affected by pressure, but it's also affected by temperature, and there's a significant effect. It's been calculated that the temperature affects the density altitude by 120 feet per 1 degree. Now that's quite a big difference from pressure, isn't it? It was 1 hectopascal per 30 feet with the pressure, but it's 120 feet per degree of temperature. So temperature is significant. So why do we care about that? The higher the density altitude, the poorer the performance, and the longer the takeoff distance, as well as the poorer the climb performance will be as well, as you learned about in the climbing and descending briefly. And there's a calculation for density altitude too. So using the data I've put up on the board here, you can calculate what the density altitude would be. First person calculator to shout it out. Will be like ridiculous, like really high.
2,700.
Cool. $2,950, did you say?
2,940, yeah.
Okay. So after taking into account the temperature, we've come up with a density altitude of close to 3,000 feet. The aeroplane's still physically taking off from an elevation of 810 feet, but it is performing as if it's at close to 3,000 feet, where the density is reduced and the takeoff distance would be much higher. When we're actually using our P-charts, we don't have to calculate this density altitude part. We do have to calculate a pressure altitude though. The graph automatically takes into account or calculates the density altitude for us. So we'll have a look at that part now. So what you do here, pause from the mass brief bring the graph up, documents, camera. And I would just start by giving an overview of the first box. Like you could do the whole chart now if you wanted to, but I think just actually going through box by box is useful. So let's consider this first box here first. This is the one that is concerned with the pressure altitude and the density altitude. So each of these lines here represents a pressure altitude, and we've got our temperatures along the bottom here as well. So let's say, just for a moment, that the temperature is 15 degrees. What I can do is go up from 15 degrees to the pressure altitude that I've calculated. This example, I'm just going to say the pressure altitude is sea level, which is indicated by this line here, where the two meet. If I draw a line horizontally across to this scale, I get a takeoff distance, approximately 320 meters. Now, what if we use the same temperature, but I increase the pressure altitude, so maybe up to 2,000 feet. So where the two intersect, I bring the ruler up, and now we've got a takeoff distance of about 400 meters. So you can see the effect that the pressure altitude is having, ignoring all other factors. The higher the pressure altitude, the greater the takeoff distance required. What about the effect of temperature? Let's say the pressure altitude is sea level, and we've just seen at 15 degrees, it was about 320 meters required. What about if the temperature really was 30 degrees? So find 30 degrees over here, where it intersects my pressure altitude line, draw a line across, and it's showing again, it's probably about 400 meters where the ruler is lining up. This shows that the higher the temperature, the higher the density altitude, and the longer the takeoff distance. Now we actually can plot all of that on the graph. So I'm not going to do that for you guys because you obviously do know how to do a P chart, but this is where you would now take this away, put your lines on there for pressure altitude, and what I would do is just draw it across to the next reference line and stop it there. Then you're going to go into your weight factor. Make sense? Okay, you don't need me to show you how to do that because you do know it, I should hope. So really, the most difficult part of this maths brief is actually going between the different media and remembering to do that, being consistent with that. It's not actually difficult to present this briefing because it's content that you delivered last semester. In the flight manual, there's also this little chart, which can be really useful to show you the effect of the temperature on your takeoff distance as well as your climb performance. So we've got the temperature up here, and we're saying for the example at Kofi Aerodrome it was 30 degrees, and we draw a line down, this red line here, to where it intersects the pressure altitude, and you calculated that was about 900 feet. And where it intersects here, we can get our percentage decrease in the rate of climb on the right hand side. So what's that, about a 25% decrease in the rate of climb at that pressure altitude with this temperature. That's quite a significant reduction in performance. And then on this side, we get our percentage increase in the takeoff distance. It's about 30%. That's a significant increase in the distance required to get to that 50 feet. Is there enough runway to do that? Well, we've got to carry on and account for all the other factors and come up with a distance and then make a decision. So let's talk about the next factor, which is weight. I think if you click once, it brings up all the stuff about weight. So maybe just pause here and talk about what you want to with weight, because you can see what's up there. It just gives them some interesting numbers to highlight how significant the effect of weight is. So I usually introduce it a little bit first. So I would say weight is, when we increase the weight, we increase the inertia of the aeroplane. And this means it's going to take longer to accelerate to our takeoff speed. So we're going to need a longer distance. Increased weight also means that if we were to get airborne at the minimum flying speed, that flying speed is higher because we need more lift. So the takeoff distance is increased by that as well. Here's some interesting figures for you. So have a look at that. It doesn't take much of an increase in weight to have a significant impact on the aircraft performance. An effect on the speed necessary to get airborne, an effect on the acceleration, and a very big effect on the distance required to get airborne. Adding a passenger on board could add another 100 metres to that distance. Now if we're taking off on a short runway like Ko-Fi or the grass runway here, that could be the difference between actually being able to get airborne safely and not. So ideally for a short field takeoff we are as light as possible. So weight increases the takeoff distance. So then you've got to remember, go back to your graph. I'm not going to keep bringing this up in the document scanner because you guys know what the graph looked like, but things to highlight is why the lines move down. Okay, so teach them that the lines move down because that's indicating lesser and lesser weight and a shorter takeoff distance. So then you will show them actually how to do this. Find your weight, what was it, 1,150? Talk them through that. Put it on here so they can see. But I'm not going to do that for you. Now we talked a little bit about wind in previous briefings, climbing and descending briefing. So what do you remember about that? You could pose a question about that, see if they remember why we take off into a headwind. It's okay to use extremes to illustrate the reasons here. I think I used extremes when we did the climbing and descending briefing. So imagine we're lined up on the runway for takeoff and there's a 60 knot headwind. That's our rotation speed. So we go through to full power and we get airborne on the spot. We would need no runway at all to get airborne. Takeoff distance is nil. Now we're not going to go flying in a 60 knot headwind, but as we get closer and closer to a wind strength that is almost the same as our rotation speed, our ground speed's reducing, and that will reduce the takeoff distance required. A tailwind is the opposite. So let's say we're lined up on the runway and we have a 10 knot tailwind. We'd have to accelerate to 10 knots across the runway at a ground speed of 10 knots just to bring the airflow to a standstill. And then we've still got to accelerate by another 60 knots to get to our rotation speed. So a ground speed at rotation will be 70 knots. And it's going to take a longer distance to get to that speed. So what do we want? We want to take off into wind. Not only does it reduce the takeoff distance required, it increases the climb performance as well. Obstacle clearance, and that's an important factor for this briefing today. As we've seen at the start of the briefing, if we take off from an aerodrome like Foxpine, could be trees at the end of it, so we want a steeper angle of climb. We do have SOP guidance around use of tailwinds. You can have a look at those SOPs in your own time, but there's a limitation that as a student you can't use a runway with tailwind unless you've been given approval to do so in writing. And there's a lot of restrictions that go with that as well. As a tangent, do you guys know what they are? Yep, so no students.
5 knots.
Yes, hence why our P chart only has 5 knot tailwind on it. Yep, anything else?
1,300 meters or something?
Yeah, at least 1,300 metres. What was that? Yeah, I think that's all of them. Are there any others, or is it just those 4, isn't it? Yeah. So just briefly mention that we do have some SOPs there. You don't have to go through them all, but probably a good idea for you guys to find them and familiarise yourself with those. So, like we discussed in the crosswind briefing, we can calculate the headwind. Now, you could go through a few examples here. You could grab out the wind component calculated graph, and I'm not going to bother because we've actually just done the briefing where we learned how to do that, but that, we probably wouldn't be doing that briefing just before this one. So grab that out. If it's a student, just one student you're presenting to, then get them to show you how to do it. If it's the whole class, then you might go through an example with the whole class. There's a rule of thumb, like the sine rule for crosswind. It's a cosine rule. 30 degrees, 45, 60 degrees. So these angles represent the angle between where the wind is coming from the runway heading in the direction you're taking off on. If it's 30 degrees, the headwind is 85%. If it's 45 degrees, 70% of the total wind is headwind. 60 degrees, what was that? I think it was, that's 50%. 90 degrees, nothing. So I like to memorise that one because then I don't have to bother with the graph. Helpful, just as the crosswind one is useful. Okay, so that's wind. So again, to read them through what the graph is showing you, put your example on there after calculating it. I think it says nil wind, doesn't it? So teach them how to account for nil wind. And then at that point, after filling out the wind, you can have a bit of a discussion on the difference between that distance to just get airborne and the distance to 50 feet. Highlight how much of a difference that is, because like honestly, sometimes it is almost double the distance required to just get airborne. So do point that out to them. So now we've got to account for some of the things that are in AC 91.3. And like I said, sometimes a manufacturer will put their own correction factors into the flight manual. We need to account for the surface type as well as the surface conditions. So I've shown you where to find these in AC 91.3, and at the end of this briefing we'll have a look at where they are in the flight manual as well. But here are the correction factors for different surface types. For metal, rolled earth, grass, as well as wet or contaminated runways. Now, we don't typically operate from metal runways, but grass we do commonly. Quite a big effect there, depending on the length of the grass. So the correction factor ranges from 10 to 25%, depending on how long the grass is. So potentially a 25% increase in the takeoff distance there. Again, that's a significant effect. Have a little bit of a discussion here about why these things increase the distances. Okay, it's all about friction, poorer acceleration. Those are key words to use on this slide. With wet runways, if they've ever driven a car into a puddle or something and they felt the deceleration, I liken it to that. So poorer acceleration, longer distance. So the worst combination is wet, long grass. So we've got to be very careful to account for those things. Potentially there, if it was wet and long grass, we might have to add 35% onto our takeoff distance. Huge. Another correction factor is slope. And here, you could ask them, hey, what happens when you get to a hill in your car and you start going up the hill? Oh, you start to slow down. So for an aeroplane trying to take off, the acceleration will be poorer, longer takeoff distance. And it's going to be the opposite for a downslope. So relate it to an everyday scenario, car on the hill or a bicycle if they don't drive. From AC 91.3, correction is 0.5% distance for each 0.1% slope. So there's an example here. I used to fly from an airstrip that had a 3% slope. So calculate the correction for that. What is it? Yeah, 15%. So we always took off downhill, so we gained the reduction in that 15%, and we always landed uphill to get the benefit of the upslope. Doesn't sound like a lot, but that slope is not even 3%. I mean, you can see the slope even out on our runways when you sat at the end of them, and that's only, what is it, like 0.64 or something, eh? So it doesn't take much of a slope to actually have a significant effect on the distance. So uphill slope, not good for a short field takeoff. It will increase the distance. Again, don't forget to keep coming back to your graph, going through that, because you're now on the back side of it, so teach them how to fill all of that out. Up to you whether you complete the graph after you've talked about slope, as in like now come down here and talk about the whole distance available versus distance required, or if you just wait until the P chart actually comes up in the briefing. I usually wait until then. So I just pause on the P chart now and we can talk about some tangent things like flat and takeoff. Again, this is something you've discussed with them, so ask them, hey, why do we use flat for takeoff? See if they remember. Discuss that with them very briefly. So it's all about shorter ground roll. But then as we learned in the climbing and descending briefing, flat reduces the rate of climb and the angle of climb. So we only really gain a benefit of it to get off the ground. So we tend to raise the flat pretty early once the aeroplane is airborne at a couple of 100 feet and a safe speed. Otherwise, it doesn't serve any purpose anymore. So run through that with them. Some aeroplanes are specifically built for short field operations, like this thing here. Does it say what it is? Because I've got no idea what that is, but just look at it. It's a beast. Definitely a short field operation machine. Big tyres, so it's not going to sink into the earth. Very big prop, huge and powerful engine, even looks like it might be turbine. High lift flaps. Looks like a pretty sturdy undercarriage. And have a look at the data down there. I think it says for takeoff 300 feet. So what's that, 90 metres, and for landing 200 feet, 60 metres. Pretty impressive, eh? We can't do that in a DA40. We wish we could. So just use this as a speaking point to add some interest to the briefing, to break it all up. Okay, so we've now accounted for all the, at least the quantifiable factors that affect the distance. And your P chart should look a bit like this. So we've come up with a distance on this side of the graph of 500 metres. On the back side there, we've taken into account the surface type, the condition, so that's whether it's wet or dry, and the slope. And we've arrived at a distance of 606 metres. That's quite a lot. But our job's not done yet. This whole calculation is pointless if we don't now compare that figure to the distance available for takeoff. And so to find that, we go back to the operational data page for Ko-Fi Aerodrome, and we take a look at what the table said the takeoff distance was. And you see I've put that into the chart here, 667 metres. So to be safe, we need to at least be able to get airborne in less distance than is available. So we need 606, and the runway is 667. So there's not much of a margin there, is there? So this is where we could do a short field takeoff. This graph itself does not calculate the distance for a short field takeoff. This is for a normal takeoff. So we can be confident that we could actually reduce this distance a little bit further by doing a short field takeoff. But our job is still not done. We've got to think about our own personal experience and personal confidence and minima. The more you practice these, the better you will get at them, and the closer you may accept these two figures being. But for now, it's a pretty new exercise for you, and you want a healthy margin. So perhaps we decide that, no, this distance is not acceptable for us today. We're not going to take off. What do we need to do? Could we offload a passenger? That would probably be the easiest thing to do. Maybe they have to get the bus. So make sure you go through those steps, because it's critical, all right? If you don't do the whole comparison with the distance available and required, and then the personal minima stuff, that's where accidents happen. I tend to talk more about it in the short field landing briefing, but take a look at the CAA accident statistics on their website. it is appalling how many of these incidents and accidents are takeoff and landing things. For example, runway excursions, going off the side of the runway, going off the end of the runway, failing to abort the takeoff, failing to go around. A huge number of the accidents that they get records for are all to do with takeoffs and landings. A little story I sometimes mention, and actually no, I'll tell that in the landing one. Okay. So we've now calculated the distance and we've made a decision based on our personal minima. We've got a good awareness of all these different factors. So let's move on. I've already talked about how your personal limits are affected, or rather your skill and your currency affect your personal limits. So you'll get plenty of practice of these throughout your training. And initially we may start on longer runways, and then as you get more confident and competent with the procedure, we may use the grass runway for you to land on as well. Decision making and awareness is huge for this exercise. Some things that we modify for the takeoff include the performance briefing. So for this we'll nominate an abort point, and we have some SOP guidance on that. We nominate an abort point that is 50% of the takeoff distance available. And we want to be at a speed 75% of the takeoff speed by that point. So for us that's 45 knots by halfway along the takeoff distance available. If we're not at that speed by that point, we abort for takeoff. Another helpful thing to mention in the performance briefing is the slightly modified procedure in the event that we have an engine failure. Now, you'll see today that initially our climb out speed is 70 knots. That is below, potentially, the glide speed. So if the engine was to fail as we're climbing out at that speed, it's going to be a reasonably prompt check forward to the gliding speed to stop the aeroplane from stalling. That's really critical. Do mention that, especially if you end up flying low inertia machines like microlights, because they stop flying like that. They don't have the punch that heavier machines do. There have been so many accidents with engine failures after takeoff where the pilots hadn't checked forward quickly enough and they just stall instantly, because you watch the airspeed, just do that. It's ridiculous. You've got to be so careful. So it's not quite that bad in a DA40, but you still got to check forward properly. Just because we're doing a short field takeoff or short field landing doesn't mean that we don't consider crosswind and gusty conditions. So it may be necessary for you to increase the rotation speed as we've just discussed. Don't just do that blindly though. You need to consider now that higher speed means longer distance. Are we still happy with the distance? Before you take off, remember we've calculated all of this inside perhaps an hour or an hour and a half before we actually go to get airborne. We need to check that the conditions are still valid that we're using. So what I tend to do in the performance briefing is check the temperature, check the QNH, check the wind. Make sure it's still valid or hasn't turned in an unfavourable direction. For example, hotter temperatures, lower QNH, less wind. Those things invalidate your calculation and might mean you actually need more runway than is available now. So we might decide not to go. Again, that is really important. So that brings us to the air exercise. We've done our performance briefing. We've talked about our abort points. We've talked about the engine failure procedure. Now the takeoff itself. We want to use all the available runway. Remember, we're interested in maximising the distance available to us. So we will backtrack to the end of the runway. We're not going to take off from Delta. We're not going to take off from Bravo. We're going to use all the available runway. So this will involve you actually getting a backtrack clearance from the tower. As a tangent instructional technique, make sure you do that as instructors. Okay? We've had a CCAT almost fail their test. In fact, no, they did fail because they didn't backtrack. They just did, we always just go from Delta or Bravo, right? And we just say, oh, well, let's pretend the runway is at this dimension. No, you do it properly. You go back to the start of the runway, because because otherwise you're giving the student permission to do the same. And they'll do that on a runway one day that isn't long enough, and they will run off the end of it. So we will use all the available runway. Once we've done our line-up checks and we've been cleared for takeoff, or we've done our takeoff call, we'll apply full power. If it's a stony surface that we're taking off on, just caution for any stones. You may want to increase the power just slowly and keep some aft elevator on. Your feet should be firmly on the brakes at this point because we want to maximize the acceleration. We can reduce the takeoff roll by first setting power and then releasing the brakes once full power has been set. We're going to rotate at 60 knots, and it pays early in the takeoff roll to check for normal acceleration. Is what we're experiencing abnormal? Are we accelerating slower than usual? That could indicate that we're actually going to need a longer distance. Perhaps we're bored. Figure out why we aren't accelerating as expected. Once we're airborne, we set the attitude forward and accelerate to the best angle speed of 70 knots, because we're going to simulate today that we've got obstacles, perhaps trees, at the departure into the runway. SOPs wise, we simulate an obstacle clearance height of 200 feet AGL, and then we clear the obstacles. At that height, we can lower the nose to accelerate to our usual speed of 80 knots, and then at a safe speed and a safe height, positive rate of climb will raise the takeoff flag. And that is our air exercise. So, pretty simple air exercise. So this briefing again I want to emphasize is largely about awareness and decision making and your ability to calculate the distance required. So far in your training, I have been taking care of performance for you. I've been doing P charts for you. Let's just say I have been. Sometimes you've introduced your students to it, but I've been taking care of that. I've been making sure that the distance has been safe, and we've been using the SOPs to ensure a safe distance when we've been taking off from Delta and Bravo. But from today onwards, when a P chart is necessary, I'm going to leave that responsibility up to you. And in the pre-flight briefing, you can tell me whether you think it's going to be safe for us to take off today. So don't forget that bit. Now you're shifting the onus away from you onto them. Okay, there needs to be that shift today. Of course, you might have to guide them through a few more P charts. They'll probably make mistakes, so really scrutinise at least those first couple to see if they're doing them correctly. Fix any mistakes, we'll guide them through how to fix them. But you're now getting them to do it. Okay, so that's the short field takeoff. Okay, so not such a bad briefing to deliver because you know the content already. Like I said, the difficult bit will be just remembering to go back and do the chart in between each factor. If you're going to do it that way, otherwise do it all in there. That is also fine. You don't have to do it this way. Do you have any questions from anything in that briefing? All right, have a 5-minute break and we'll carry on. What time are we supposed to be here to?
12, 10 I think.
Okay, cool. Heaps time.